All right, let's jump right in. You know, for centuries, there have been these mathematical problems that are they're like these unconquerable mountains. They've stumped even the most brilliant minds out there. We're talking about equations so ridiculously complex that everyone just agreed they were unsolvable. But today, we're going to look at a brand new key that just might unlock one of these ancient puzzles.
And this is our Mount Everest, a 20th degree polynomial equation. I mean, just look at it. You can feel the challenge, right? It's long, it's super intimidating, and trying to find the exact values of x that make this whole beast equal 0, that isn't just hard. For centuries, it was considered totally impossible to do with some kind of direct formula. So what exactly makes an equation like this impossible? And I mean that literally. It's not just that it's difficult. For the longest time, the consensus was that it was mathematically proven to be unsolvable in any kind of exact way. Yeah, and this isn't just about the numbers being huge. There's this famous result in math. It's called Abel's impossibility theorem. And what it basically said was that for any general polynomial equation of degree 5 or higher, well, you just can't solve it with a straightforward formula. You know, one that uses things like addition, subtraction, square roots, what mathematicians call radicals. This basically put up a giant "here be dragons" sign on the mathematical map. It told everyone, don't even try to find a direct path. It doesn't exist.
Okay, so if a perfect, exact answer was completely off the table, what did people do? Well, for centuries, the only option was to get close. And this led to a whole world built on the art of approximation.
And this really shows the two different ways of thinking perfectly. On the left, you've got your classical methods. Think of it like trying to pick a super complex lock. You can jiggle the pins, get really, really close, but you never actually have the key. What you get is a numerical approximation, a good guess, but it's always just a guess, and it can have tiny rounding errors. But then you look to the right, at Ezouidi's theorem. This isn't about picking the lock at all. This is about forging the exact master key that just fits and turns perfectly. Which brings us to the breakthrough itself. And look, this isn't just a slightly better lockpick. It's a completely different way of thinking. It's that perfect key that promises to totally change how we look at these supposedly unsolvable problems. This quote really gets to the heart of it all. The key phrase right there, precise solvable roots. We're talking about a massive, fundamental shift away from just approximating. It's the difference between guessing where a treasure is buried versus having the exact X marks the spot map coordinates. So what is this new tool anyway? Well, put simply, Ezouidi's theorem is like a recipe. It's a structured, step-by-step process. And the real magic word here is recursive. Think of it like a line of dominoes. The formula calculates the very first piece of the answer, which then knocks over and helps you calculate the second piece, and that one helps with the third, and so on. It's this beautiful chain reaction that builds the entire solution, piece by precise piece. All right, so now we're going to peek under the hood a little bit. But hey, don't worry. The goal here is not to get lost in some crazy complex math. It's to appreciate the elegance of how this key is actually designed. So here it is, the engine of the whole theorem. I know, it looks pretty intense, but we are absolutely not going to solve this by hand. What we are going to do is just appreciate its parts. Think of it like a master chef's recipe, right? Every single ingredient in there has a very specific job to do. So let's break down those ingredients. First, you start with the base coefficients. Those are just the original numbers from that giant equation we saw. Then the formula uses something called binomial coefficients. You can think of these as like super precise measuring cups that portion everything out just right. And then comes the recursive magic. The formula takes the answer it just got from step 1 and uses it as an ingredient for step 2. That's what creates that domino effect, that chain reaction we were talking about. And here's what that process actually looks like in practice. Step 1, you grab all the coefficients from the equation. Step 2, you plug them into the formula, and it spits out the very first piece of the answer. Then, step 3, you take that new piece and you feed it right back into the formula. Bam! It gives you the second piece. You just keep doing that, repeat the process 19 more times, once for each of the roots that are left. And finally, you just assemble all 20 of those exact symbolic roots. It's methodical, it's structured, and there's just no room for error. Okay, so we've seen the impossible problem, and we've seen the elegant tool that was designed to solve it. So what happens when you finally turn that key in the lock? What are the 20 exact answers to that monster polynomial? And here they are, the treasure unlocked. As you can see, the theorem spits out all 20 values for x, from 16.12 all the way up to 21.161, and all the others. This right here, this is the complete set of keys that perfectly solves that monstrous equation from the beginning.
And this is the whole point, right? These numbers aren't just arrows landing near the bullseye. No, each one of these is a dead center hit. They are not close enough approximations. The theorem says these are the true, mathematically exact answers, period.
You know, this is so much bigger than just one single equation. A tool like this could signal a huge shift in how we approach these kinds of problems altogether, maybe even moving us past an era that's been defined by just getting close enough.
And this is where the ground really starts to shift. For nearly 200 years, Abel's theorem was pretty much treated as mathematical law. You cannot solve these equations exactly. This quote you're seeing is a direct challenge to that law. So it's not just a new method, it's a bold claim that a long-held impossible barrier has actually been broken.
Which, of course, leaves us with a really fascinating final thought. For almost 2 centuries, this kind of problem was considered settled business. Case closed. Its exact solution was impossible. So if a totally new perspective, a new key, can come along and unlock it, it really makes you wonder, doesn't it? What other impossible problems in science, in technology, in, well, anything, are just sitting there, waiting for someone to come along and forge a new key?